thank you very much. Hello to everyone. My name is Sebastian Passanante. I'm from Buenos Aires, Argentina. And today I'm going to talk about our work, which is about the magnetocaloric effect in nanocrystalline bilayer thin films. We use manganite as the material. So I have a little problem. Yeah, that's okay. First of all, let's talk about what is the magnetocaloric effect. The magnetocaloric effect is known as the adiabatic temperature change, which happens in a material when a magnetic field is applied. You can also think about it as the isothermal magnetic entropy change in a material, obviously, when a magnetic field is applied. The main motivation behind this topic is that you can think, build and design new refrigerators for room temperature, which replace the actual refrigerators. And they come with some advantages like a greater efficiency. They can be more compact, a lower energy consumption, which is important nowadays, and more eco-friendly with the environment. So in this work, I'm gonna characterize the films as using an indirect measurement of the magnetocaloric effect. I'm going to calculate this magnetic entropy change using this thermodynamic relationship from Maxwell. And what are you looking when you work with a magnetocaloric material? There are a list of some parameters that are important. The first is a suitable Curie temperature. This is where the magnetocaloric effect has its maximum effect. And you want that this effect has to be the more large possible. Another thing which is important, especially in this talk, is you want this curve to be wider as possible. This is defined as a mid-height temperature. This represents the temperature range where the magnetocaloric effect is important for this material. It's also like the temperature range where a magnetic refrigerator could work with this kind of material. And as you are going to work with magnetization and the magnetization cycling, you need to minimize the magnetic hysteresis. In the magnetocaloric community, we work with figures of merit. The more important figure of merit is the refrigerant capacity, and is calculated as the area of the integral of this curve, and physically represents the amount of heat transferred between the cold and the hot sinks in a thermodynamical ideal cycle. So as to resume some of the things that is known in the magnetocaloric world, when you work with a bulk and ferromagnetic material, you have an entropy change curve like this in red, which is a narrow curve. The delta T, the temperature range where you can operate, is narrow, is about 20 Kelvin. If you want to broaden this curve to get a material that can be used in a more extensive temperature range, you can grow thin films of this material. When you do this, you are reducing the maximum of this entropy change, but you can broaden this curve a lot. There are some other way to do this is by using composite. The problem with composite is that you are working with bulk, so sometimes there is a little overlapping between the curves, and you can broaden this curve, this temperature range. So in order to improve this and have a better, larger temperature range when the magnetocaloric effects can be developed, you can think about what is a bilayer. So we are going to study a system of 2 layers of thin films, and you can have a more stable region where the magnetocaloric effects is important. So we grow by post layer deposition, a series of films. These are the growth conditions. So we grow with 2 different layers. We are working with LSMO. One layer is for a concentration of strontium of 0.12, and the other layer is for a concentration of 0.25. We grow this bilayer, and then we grow a similar with changing the stacking order. We grow these films over silicon substrate. So the growth is polycrystalline with a grain size of 40 nanometers. In the literature, you can find this as nanocrystalline. The stacking order is important for us because we knew for another work that for epitaxial LSMO thin films, the stacking order matters and can change the magnetic properties and magnetocaloric properties. And also the results are going to be compared with single layer thin films of similar thickness. Here are the magnetic measurements. All of these curves are normalized at their magnetization at 50 kelvins. For the single layers, we found paramagnetic to ferromagnetic transition that we can observe this transition also in the bilayers. A transition here in 175 kelvins, which correspond to the layer of 0.12 and corresponding to the layer of 0.25 here at room temperature. So in the bilayers, we can see the 2 transitions. And in talking about the stacking order, we didn't find any difference between the magnetic properties of the bilayers. So in this case, the nanocrystalline, the magnetism properties does not been affected by how you stack the layers. Here are the magnetocaloric effects results. Here I present you the variation of, the magnetic entropy change. You can see as a peak and a single peak for the single layer thin films. The peaks are centered their transitions, and you can watch as the bilayers present 2 different transitions, one corresponding to the 0.12 layer and the other corresponding to the 0.25 layer. And as you can see in this table, you can watch how happens with the temperature range where the magnetocaloric effect is important. For bulk material of this manganite, you have a range of 20 kelvins. When you grow your thin films, this temperature range is about 60, 70 kelvins. And with the bilayers, you have this temperature range you can grow to 200 Kelvin. This is a range of temperature where the magnetocaloric effect is important. This also brings an increment of the refrigerant capacity, as you can see from in comparison with the single layer thin films. So this is a magnetocaloric thinking as an improvement. And talking about the stacking order, there is no difference between the stacking order of layers. So this is an improvement in terms of the epitaxial case where the order was important. Now it's not. So we can think to incorporate some different layers. And if we can compare this with nanocomposite, yes, of nano bulk. In this case, it's a work from Picala. They found that they can distinguish between the two peaks. In our bilayers, the additional order, because we are working with layers, let us resolve the two transitions, the two different peaks. And we also found a table-like zone. This is important in magnetocaloric effect because it's a zone where the effect does not depend in temperature. So we found that it's possible to combine the advantages of thin films and nanocomposite in a unique system, which is very versatile. And we can add a non-magnetocaloric layer, for example, for heat transfers or heat dissipation. And now we're working in a third layer here to improve this table-like zone. So finally, as a conclusion, we can get a wider temperature range of operation with these bilayers and have an improvement in the refrigerant capacity. We have a system which is simple to adapt to different applications. We saw that the stacking order does not affect in this nanocrystalline case, and we could combine the advantages of nanocomposite and thin films. So thank you for your attention. And if you want to talk about magnetocaloric, here's my email.
Thank you very much, Sebastian. I don't know if we have any questions. If they're not, I'm going to start with one. It's not clear for me what would be the nanocomposites that you are trying to combine with the thin films. I
said they are nanocomposite. They are bulk of similar manganites, LSMO and LCMO. The important here is that the disorder you have in a nanocomposite don't let you distinguish between the two transitions from the different phases. In a bilayer, you can see when the transition of one of the layer and then the transition of the other layer.
So the nanocomposite would be like a solid mixture. I mean,
yes,
little grains of both.
You have,
okay.
You are broadening so much the effect, and you can have the maximum in each temperature.
Great, thank you. Alberto has a question now.
Yes.
Hi, Sebastian.
Hi, Alberto.
I have a question about the thickness of the bilayers. So of each of the layers, does it matter? Do you see a dependence on that?
In that range is not so important. It's important for things like the saturations, but it's not so important. But we want to reduce the thickness to see what happened at the interfaces.
Right. And I'm also curious because if you keep adding layers, right, in principle, this will look even more and more broader. But at some point, the thickness of the total, heterostructure is going to play a role.
Yes, yes, I think yes. I am working like in this. I couldn't explore that path, but it's in my list to do.
Great talk, really interesting. Thank you.
Thank you.
Thank you very much, Sebastian. I think
Thank you, Patricia.
If anybody has any other question, can go to GatherTown and find Sebastian.